The year was 1977. NASA launched two of the most ambitious explorers ever built, Voyager 1 and 2, on a journey that would change our view of the solar system forever. But this mission wasn't just about lifting a probe off to some orbit. It was about an opportunity so rare, so perfectly timed, it only happens once every 175 years. The key was a precise celestial alignment. The four gas giants, Jupiter, Saturn, Uranus, and Neptune, had lined up like a string of cosmic jewelries. This unique planetary geometry gave rise to what NASA called the Grand Tour. The plan was simple yet bold. Launch one spacecraft and use the gravity assist maneuver to slingshot it to the next. To seize this opportunity, NASA launched two identical probes. Voyager 2 went first on August 20, 1977, setting its course for the Grand Tour. Then, just 16 days later, Voyager 1 was launched on a slightly faster trajectory. Both of them were launched using Titan IIIe Centaur rockets. This is how a gravity assist looks like. But how does it work? To understand it, let's examine what happens if we switch to the planet's reference frame. In this frame, the planet is staying still. Relative to the planet, a probe would approach and leave the planet with the same speed. Switching back to the world frame means that the probe now has an additional speed from the planet movement. Gravity assist can also be used to slow the probe down. In order to do this, the probe must approach the planet from the opposite direction, let's say from the front of the planet. Voyager was not the only mission that made use of gravity assist maneuver. Several years before, the Apollo spacecraft comes to the moon in the opposite direction to the moon's velocity vector. It helped the spacecraft to slow down and conserve precious fuel. Other notable missions that used gravity assist maneuver were Luna 3 from USSR, Pioneer 10 and 11, Mariner 10, New Horizons, and Cassini. The real excitement began at Jupiter. The two Voyagers arrived in 1979 and immediately sent back unprecedented views of Jupiter's building atmosphere. The most prominent feature of Jupiter is the massive Great Red Spot. It is a massive anticyclonic storm, characterized by counterclockwise rotation and high pressure at its center. When discovered by Voyager, it spanned about 24,000 kilometers wide, with wind speed exceeding 400 kilometers per hour. Internal heat powers convection, rising warmer gases that sustain the vortex. Smaller eddies and storms merge into it, providing energy and explaining size fluctuations. Jupiter's moons also had their own surprises. On Io, Voyager probes discovered massive plumes of gas and dust erupting hundreds of kilometers high. This was the first evidence of active volcanoes found anywhere in the solar system besides Earth. Io's volcanic activity is very different from Earth's. The tidal force from Jupiter's gravity constantly squeezes and stretches its internal materials, creating a hot liquid rock like Earth's magma, thus causing volcanic activity. They also photographed Europa's startlingly smooth, ice-covered surface, crisscrossed by strange lines. Scientists theorized this was a relatively thin crust of ice floating atop a liquid water ocean, with possibly life underneath it. The encounter at Saturn, just several months apart, shattered all prior beliefs about its magnificent rings. Instead of a few simple bands, the Voyagers revealed a system composed of thousands of individual bands, proving their complexity. From afar, Saturn's rings look like solid homogeneous rings. But if you zoom in, these rings are more like an asteroid field. There are ice particles, chunks of material, boulders, even micrometer-sized dust. You might wonder why these rings do not become moons. Saturn's moons lie outside its Roche limit. Inside Roche limit, which is about 117,000 kilometers from Saturn's core, the tidal force from Saturn's gravitational pull prevents the ring particles from aggregating into a moon. Then they made flybys close to the large moon Titan. It confirmed that Titan has a thick orange atmosphere that comes from its hydrocarbon abundance. From here, Voyager 1's path is directed out of the ecliptic plane toward interstellar space. Only Voyager 2 continued the grand tour. Arriving at Uranus in 1986, it was the first and only spacecraft to visit this bizarre sideways tilted planet. Yes, you heard that right. Uranus is orbiting sideways like a rolling ball, with one of the poles facing the Sun. The prevailing explanation involves a massive collision early in the solar system's history. An Earth-sized protoplanet struck the young Uranus at a glancing angle, knocking its axis over and scattering the material that formed its moons and faint rings. The final encounter in 1989 at Neptune was a scientific finale. The atmosphere was surprisingly active, featuring the Great Dark Spot, a huge anticyclone storm driven by winds exceeding 2,000 km per hour. It appears as a dark oval due to a hole in the planet's upper methane cloud deck, with Neptune's internal heat acting as a power source. It is faster than the red spot because of the steeper temperature gradient from much colder Neptune internals. Neptune's largest moon, Titan, proved equally astonishing. Although its temperature is very close to the absolute zero, there are active nitrogen geysers erupting from its ultra-cold surface, a sign of ongoing geologic activity far from the Sun's warmth. After that flyby, Voyager 2, like its twin, used its final gravity assist to leave the solar system, officially ending the planetary phase of the Grand Tour. After completing the Grand Tour, the Voyager mission didn't end. Its mandate simply expanded. The probes were now on the final and most profound leg of their journey, the Interstellar Mission. In 2012, Voyager 1 reached a place where no one has gone before. It crossed the heliopause and entered the interstellar medium. It became the first human-made object in history to venture into the space between the stars. Voyager 2 followed in 2018. Today, these two tiny probes are sending back data on the density of interstellar plasma and the intensity of cosmic rays. But as the decades pass, the power is dwindling. The RTGs are decaying, forcing engineers on Earth to carefully turn off instruments, one by one, to conserve the final trickle of power for the most essential systems. The mission is expected to finally fall silent sometime in the late 2020s. Before they go silent, there is one last piece of the mission to consider, one that ensures the Voyagers carry a message long after our instruments can hear them. Attached to the side of both probes is the Golden Record, a 12-inch gold-plated copper phonograph. It is humanity's message to any intelligent alien life that might one day intercept the craft. Etched onto the cover are diagrams showing how to play the record, where the Earth is located, and the speed at which it should be played. The record itself contains 115 images, sounds of nature, spoken greetings in 55 ancient and modern languages, and a selection of music ranging from Bach to Chuck Berry. The chance of the Voyagers ever being found in the vastness of the galaxy is very small, almost close to zero. But the Golden Record serves a more immediate purpose. It represents a profound snapshot of humanity at the moment when we began our voyage to the stars. They were launched to show our planetary neighbors. They stayed to show the edge of our home, and they carry a golden, silent message into eternity. Thanks for watching. Please support this channel by hitting the subscribe button. And don't forget to leave your thoughts in the comment section.